Assalamu alaikum, girls. We're going to resume with the Argand diagram. So we covered a bit of arithmetic involving complex numbers, some square root identities. Today we're going to be observing the Argand diagram, and this is like the Cartesian plane that we use for coordinates. But what we use for complex numbers is what's called the Argand diagram. And to start, we're going to look at things from a perspective we already understand. Now, we know what a number line is, okay? A number line, we can have 0 here, 1, 2, we can have negative numbers, and we can even have decimal numbers, fractional numbers, so numbers in between these numbers, okay? And if you remember the introduction to this course, we had numbers placed into categories. So numbers placed into categories meaning real numbers, complex numbers, imaginary numbers, etc., etc. Well, what we're looking at in this case is we've already understood that there are things called imaginary numbers or complex numbers, and someone in the 17th century decided that he would like to express them in some sort of graphical representation as well, and he did so by observing the number line and decided, well, what if we add a new axis? So that's what I'm drawing here, a new axis, and we will call this axis the imaginary axis. Okay, so this here is the imaginary number line, or the imaginary axis, whatever you want to call it. So imaginary number line. And now, by adding a new dimension, so for example, we only understand the real number line in one dimension. But now, adding a new dimension in terms of imaginary numbers, we get like this very similar concept to the Cartesian plane. The only difference is how an Argand, and this is called the Argand diagram. The only difference between Cartesian and Argand diagram is certain properties we can apply here. Okay, now how do we read and understand an Argand diagram? Well, basically, the Argand diagram represents all the imaginary numbers. So basically, this is like where I would be, this is where 2i would be, this is where 3i would be, negative I, negative 2i, negative 3i. But since we already understand that this is the imaginary line, you don't actually have to write the I. We can just write 1, 2, 3. But we know that this represents 3i. This is negative 1, negative 2, negative 3. So that's the Argand diagram in its introduction, in its basic form. So how did this fellow, I forgot his name, I think that's definitely his surname, but I forgot his first name. But how did he decide that we're going to be utilizing the Argand diagram to express complex numbers? Well, he was on one. I don't know the exact story, but like he was looking at the number line, he was looking at the real numbers, and he came up with a way that sort of made sense. So if we multiply by I, that's the same as 1i. Well, what happens is we get 90-degree anti-clockwise rotation. This fact here is a very important thing. Okay, so if I take 1, if I take the number 1 and I multiply I to it, I get I. All right, and this here represents 1i, this point here. This is 1i. But like I said earlier, we don't need to write the y because we already understand this line is imaginary. But there we go, we have 1 times I. And I'm just going to leave that up here. So that's 1 times I. And now, what I'm going to do, I'm going to multiply this by I. So essentially, we're going to do I times I. We're going to see what happens here. So what's I times I? We are aware that this will equal to negative 1. And look what happens. We get a 90-degree anti-clockwise rotation to negative 1. So now my point has transformed from I to negative 1. And it all makes sense. And now I'm going to take this number, I'm going to multiply it by I. So negative 1 times I will get negative I. And this corresponds to this value right here, -1 on the imaginary axis. So that will be an anti-clockwise rotation to -1. And then finally, this number, -I times I equals +1. And look at that, we came around full circle, landed back at our original position. Okay, so basically what we can understand from this not discovery, but this interpretation of complex numbers by Mr. Argand is that it allows us to see some interesting geometrical applications which become quite useful for solving certain problems. Okay, so this is your first dive into expressing complex numbers on a diagram, and we will call it the Argand diagram. So let's look at some complex numbers and start plotting them. Okay, so we've got here, plot the following complex numbers on an Argand diagram. We have all these points. What I'm going to do, because there's so many dots on this, I'm just going to do every second one as a number. We don't need too many. And here. Alright, that's plenty. Notice how I've labeled the axes. I've basically called them the real axis and the imaginary axis. Maybe that will give you a hint as to how we're going to do it. Well, look at the first point. A2 plus 3i. So basically, if z equals x plus iy, this is the real coordinate, and this is the imaginary coordinate. That's a nice, easy way to think about it. So essentially, on a complex plane, you could think of 2 plus 3i as 2, 3. All right, and that's literally it. It's actually, the complex number is basically a representation of a coordinate on the Argand diagram. So now I can take my point 2, 3. Wait, let me just line it up. All right, so that means our dot is right there. So that there is the point A, 2, 3. I can also write it as A2 plus 3i. Both are correct. But for the sake of understanding complex numbers, I'm going to write it like this. Now looking at the next point, we have -4, -1. Okay, I like to transform them into coordinates just so I can easily plot them. So that means -4, -1. I will take this, -4, -1. I might need to stretch that just a tad. So -4, -1. We'll plot the point B right here. And we can express the complex number like so. All right, so far so good. The next one, we have C2i. Okay, this one, it's got a hidden coordinate. Well, when one of the values are not present, so if the real part is not present, then you put in place of it a 0. If the imaginary part is not present, then you put 0i, or you put a 0 for that as well. All right, so that means we're going to go to, we're going to move vertically 0 units. So if I put it there, it'll be stuck. So let me just put it aside. And then we go to 2. So we're basically intersecting with the imaginary axis. And that point there is C02. And there we go. And the last one, -3, +2. All right, so we're going to take this, -3, +2. I didn't have to move that much. +2, there we go. That is our point D. So as you can see, complex number representation on an Argand diagram is very, very straightforward. So hopefully you got all that with no issues. All right, now let's move on to the next section. This section is observing the behavior of complex numbers and their conjugates. So let me just quickly plot these in. Okay, so we have our imaginary axis, our real axis, and we're going to plot these and their complex conjugates. All right, so the first one, the conjugate of 2 plus 3i, we're going to write z1 bar because it's going to be the complex conjugate of that, is 2 minus 3i. And I'm going to plot these both on the same graph, and you're going to see how it looks graphically. So we come across here and here. So 2, 3. This is Z1. Well, if we look at this, our complex conjugate will be directly below it. This is Z1 bar. So complex conjugates have this property where they retain the same real value, but the imaginary value is what changes. So there's an identity here that you can recognize graphically, and I'll write that here real quick. Complex conjugates reflect about the real axis. Okay, so if you know a complex conjugate, you know its conjugate is directly in the opposite space with respect to the real axis. So let's look at the next one. Z2 equals -4 negative I. So Z2 bar equals -4 plus I. And if we plot this, we've got -4, and then we've got -1. So that's Z2. So Z2 is -4, -1. Well, this complex conjugate, notice I'm only going to move the horizontal line, and it reflects exactly in the real axis, and it's not 2, it's 1, sorry. So there we go. That means Z2 bar is over here. And you can see it's a direct reflection through the real axis. And then finally, we have Z3 equals 2i. So let's plot that point real quick. 2i is right there. So that's Z3. Well, since we understand that we only reflect the horizontal line, then we're going to bring it down to here. And that there will be Z3 bar. So graphically, going by this statement here, that also tells me that the coordinate is now Z3 bar equals -2i. All right, and there we have it. You can see all the conjugates, they are reflected from each other about the real axis. Nice and straightforward. Okay, so coming into the next section, the modulus argument form. What I'll do, I'll just split this into a second video, so just give me a moment, please.